Again, we are going to start with the thin layer approximation, right? So the entire section is in the thin layer approximation. And in the thin layer approximation, we have u times du dx plus v times du dy. And it is driven by the pressure gradient, which we know is ue times due dx. So this is the same no matter it's a similarity solution or not, right? Because this term has to balance the pressure gradient immediately outside the boundary layer, no matter if it's a similarity solution or not. And then we have plus, in the laminar case, is the laminar viscosity times the the second order derivative of velocity. So now we put that into streamline function form. In the streamline function, u is partial phi partial y, and let's keep these derivatives of u still to be derivatives of u. Now the v becomes a negative of partial phi partial y, and a partial phi partial x, sorry. And we still keep the velocity to be the same. This is because if you remember how we did in the similarity solutions, ultimately we solved 3 coupled ODEs. And one of the variables is basically u itself. So instead of writing out partial phi partial x, in this case partial phi partial y, and then at the very end say, okay, let's use another variable to designate partial phi partial y. Let's just keep the u throughout the equation. This is equal to that plus nu times, let's still set it to be the second order derivative.